Hello. Okay. Hello everyone. I am Suvrat Mehta, and today we'll be discussing the problems of CodeChef Starters 208. So, let's start with the discussion. So, problem A, alternate jumps. There are n lily pads arranged in a line. They are numbered 1 to n from left to right. A frog is initially standing on lily pad n. The frog loves to jump, so it will perform a sequence of n minus 1 jumps with alternating directions as follows. First, jump to the lily pad n minus 1 positions to the left of its current position. Next, jump to the lily pad n minus 2 positions to the right of its current position. Next, n minus 3 position to the left of its current position. More formally, in the ith jump, if I is odd, the frog will jump to the lily pad n minus I positions to the left of the current position, and if I is even, then the frog will jump to the lily pad n minus I positions to the right of its current position. It can be proved that all of the frog's jumps are valid, that is, it will always be on one of the lily pads from 1 to n. You are given n, can you find the number of final lily pad the frog will end up at? So, the constraints are t is still 100 and n is still 100, so expected time complexity could be a maximum of n square. So basically, problem A, what the problem says is a frog is initially standing on the lily pad n. So initially the position is n. Then it makes n minus 1 jumps, and on the first jump it will go n minus I, on if I is odd, on the ith jump, if I is odd, the frog will jump to the n minus to the lily pad n minus I positions to the left of its current position. So basically, uh, on jump 1 it will move left n minus 1 times. On jump 2 it will move right n minus 2 times. On jump 3 it will move left n minus 3 times, and so on. And we need to tell the final position after jump n minus 1. So let's see the test cases. So let's solve for when n equal to 2. So n equal to 2. After the first jump, it will move left with 1. So 2. Then after the first jump, it will come at 1. Then it will go right. Okay, n minus 1 is only 1. So 1 would be the answer. Only one jump. Then n equal to 3. Initially at 3. Then 3 minus 1, 2 towards the left. So towards the left 2. So 1. Then the next jump will be towards the right 1. So 2. This is the position and this is the jump. So the final answer for this would be 2. Then the next is n equal to 5. So initially position 5, then towards left 4, then towards right 3, then towards left 2, then towards right 1. So this will be 3. The final answer for this will be 3. Then the next test case is n equal to 6. So position initially 6, then towards left 5, then towards right 4, then towards left 3, then towards right 2, then towards left 1. So final answer again is 3. So the solution to this problem would be we can simply just directly implement these jumps. So how can we do that? Just like how we solved in the test cases, we can simply maintain a position variable and then we can run a for loop, and we can do the operations. If I is odd, then we can simply we can update the position to position minus n minus I, else we can update the position to position plus n minus I, because this will be moving left and this will be moving right. So after this for loop, the final position would be our answer. So that was the solution for the problem A. I'll show you guys the code. So basically, there are t test cases, and for each test case, I take the input n. Initially, the position is n, and then I perform the n minus 1 moves or jumps. So if I is odd, then position will be shifted towards left by n minus I, else the position is shifted towards right by n minus I, and then in the end, I just print out the position final. So that was the solution for problem A. Let's move on to problem B. So Chef is problem B is Sabotage. Chef is participating in a programming competition. Currently, he has a score of X. There are n participants other than Chef. The ith of these participants has a score of AI. Chef's rank in the contest is determined as follows. Count the number of indices I such that AI is greater than X. Let this count be R. Then Chef's rank is equal to R plus 1. Chef would like to improve his rank, so he decides to sabotage his opponents. A sabotage operation is defined as follows. Choose an index I and do both of the following. Set AI to 0 and add 100 to X, that is increase Chef's score by 100. Since there's not much time remaining, Chef can perform the sabotage operation at most k times, find the minimum possible rank Chef can achieve at the end. And the constraints for this test for this question are t is less than equal to 500 and n is less than equal to 500, and we are not given any constraint on the sum over n. So I think maximum of maybe n square could work. If we write a solution in O of n square, then that overall time complexity would be O of t into n square. That would be 500 cube operations. So that would be 125 into 10 to the power 6, which is 1.25 into 10 to the power 8. This may or may not pass because time limit is 1 seconds, and in 1 second we can only do 1E8 operations. So this may or may not pass. So we need to find solutions like n log n or n log square n. We need to find n log n. We cannot do n square. So problem B. So basically, we have a initial score that is X, and we have an array A with A1, A2 till AN, and our rank is number, basically count of indices I such that AI is greater than X. So uh, number of AI that are greater than score plus 1 would be the rank. And the operations that we are allowed to perform is basically in an operation we can set some AI to 0 and increase our score by 100. So this is the operation that we can do a maximum of k times. And our goal is to minimize rank. So in order to minimize rank, we need to basically minimize this term. Number of minimize number of AI that are greater than score. Sorry, greater than. final score. Since we need to minimize the final rank. Since we need to minimize final rank, hence here we need to count the number of AI that are greater than final score, because that would give us the final rank. So in order to minimize the final rank, we need to we need to count the number of AI that are greater than final score. So let's see the test cases first. So the first test case is 4, 150. So basically n, then x, and then k. So x is the initial score and k is the maximum number of operations. So test case 1, uh, n equal to 4, x equal to 150, and k equal to 1. And the array is 250, 375, 509, 12. 250, 375, 509, and 12. And the constraints are x and ai are till 10,000 and k is always less than equal to n. So basically, we have x equal to 150, right? So what we can do is, and since we can only perform one operation, what we can do is we can remove this element, make it 0, and now our x becomes 250. And our rank would be, since only one element is now greater than 250, so answer would be 2. Since rank would be number of elements greater than 250 plus 1. So the answer for first test case is 2. Then the next test case, same, but now we have two operations. So after the first operation, our array looked like this, right? Sorry. Our array looked like this. So now what we can do is, we can now make this element 0 and now our score becomes 350. And since there are no further elements greater than 350 available in the array, so our answer becomes 0, 1. Then the next test case is 5, 4, 1, 5, 3. Let me take 5, 4, 1, 5, 3, and 5, 3, 2, 5, 1, 2, 3, 2, 5, 2, 3, 6, 3, 2, 0, 7, 8, 9. So basically, initially our score is 415, and what in the first operation what we can do is we can make this 0 and then our score becomes 515. Then we can make this 0 and our score becomes 615. And then we can make this 0 and then our score becomes 715. And basically in the end there is still one uh, number that is greater than 415, so the final rank would be 2. So the answer for this test case is 2. We can make a slight greedy observation here. Basically, we can always perform the operation on the highest element. Why? Basically, because it would be for us to have a score greater than the highest element. It would be we need to perform the most number of operations. So basically, since initially 6320 was the highest number, right? So we can tell that 6320 uh, getting a score more than 6320 is currently the most difficult thing for us. We need the most number of operations for that. So what we can do is basically uh, shift this, basically apply operation on this element and make this 0, so that now lesser numbers are available in the array that we might exceed after the operations. So another observation that we can make is we need to minimize number of AI that are greater than final score, right? And since we can perform a maximum of k operations, and the operations are like good for us, basically, since they will be transforming one AI to 0, and they will also be increasing our score by 100. So basically we will always do all k operations. We will always do all k operations. So basically, if we know that we will always do all k operations, we can remove this from our equation, and now the final score simply becomes x plus 100 into k. And now we need to simply minimize the number of AI that are greater than x plus 100 into k after performing k operations. Basically, that means after making k element 0. So uh, we can rewrite our new problem. We need to minimize the number of elements greater than x plus 100 into k after making k element 0. So basically now this is a pretty obvious some new problem that we have got. Basically, we have an array and we can make some k element 0 in that array, and we need to minimize the number of elements that are greater than x plus 100k. So what we can do is we can find the count of number of elements greater than x plus 100k, and once we have found this count, basically our answer would just be count minus k, or 0, or 1 actually. So basically, if count minus k is going negative, then negative or 0, then our answer would be 1. Since basically count would be the number of elements that are greater than x plus 100k, right? So let's take some example. Let's take this test case only. So 250, 375, 509, and 12. And x is 150 and k is 1. So basically, initially the count would be 1, 2, and 3 elements greater than 150. And since we have only one operation, sorry. Count is number of elements greater than x plus 100k. So x plus 100k in this problem would be 150 plus 100, 250. And the number of elements greater than 250 would be just 2. So count would be initially 2, and then we have one more operation that we can perform. So what we can do is basically, since we know that there are two elements greater than 250, right? So we can make one of them as 0. So we can just make one of them as 0, and then our answer would be count minus k is the new number of elements that are greater than x plus 100k, and plus 1 would be the rank. So count minus k plus 1, actually here also count minus k plus 1. Now in the second test case, what happens is 250, 375, 509, and 12, and x is 150, k is 2. So basically now x plus 100k becomes 200 plus 150, 350, and the number of elements greater than 350 would be 2. So count initially is 2, but we have k as 2 as well. So count minus k plus 1 would be 2 minus 2 plus 1. So 1. So second test case, the answer would be 1. Now, basically, let's say if we had k is equal to 3 in this way, in this test case. So what would have happened is this would have become 0. And 0 cannot be the answer, right? Because rank would be minimum 1. We cannot go lesser than 1 in rank. So basically what is happening is we only had two elements which were greater than x plus 100k, but we performed three operations. So basically we made this 0, we made this 0, and we made another number 0. So let's say we could have made this 0 or this 0. So so basically that means if count minus k plus 1 is less than equal to 0, then no element greater than x plus 100k is left. Basically, we removed all the elements that were greater than x plus 100k. So in this case, the answer would simply be 1, rank 1. So what we can do is we can make the answer is equal to maximum of 1 comma count minus k plus 1. Since if this value becomes negative or 0, then this would be the answer, else this would be the answer. So, and finding out count is fairly simple. We can just run a for loop. If AI is greater than x plus 100k, then we do simply count plus plus. So, and the time complexity for this for loop would be O of n. So overall solution would be in O of n only. I'll show you guys the code. So I take input nxk, and then val is the final score that you will achieve, x plus 100k, and we need to find the count. So this for loop, if v of I is greater than val, just ct plus plus, and then the answer would be maximum of 1 and ct minus k plus 1. So this was problem B. Let's move on to problem C. So problem C is GCND. The greatest common non-divisor of two positive integers x and y satisfying x greater than equal to 5 and y greater than equal to 5, denoted GCND x comma y is defined to be the largest positive integer z satisfying the following conditions. Z is less than equal to x or z is less than equal to y, and x is not a multiple of z and y is not a multiple of z. It can be proved that as long as x and y are both greater than equal to 5, GCND x comma y always exists. You are given an array A of length n such that AI is from 5 to 10, 1e7, and for each I from 1 to n, your task is to compute the maximum GCND of some two elements of the array. So basically, we need to find the maximum possible value of GCND of AI and AJ for all pairs I, comma j. And the constraints for this problem is uh, test case are 1e4 and n is given till 2e5, but we also have sum of n over all test cases won't exceed 2e5. So basically the expected time complexity for this problem could be O of n or O of n log n, because O of n square would be 10 to the power 10 operations which would exceed our time limit, since we can only do 1e8 operations in 1 second. So Problem C. Basically, first we have a definition in this problem, definition of GCND x comma y. So GCND, basically first the full form of this is greatest common non-divisor, and this is defined to be the largest positive integer z satisfying the following conditions. So z is less than equal to x or z is less than equal to y. So equal to z, and z would be less than equal to x or z would be less than equal to y. So z might be less than any of these. There is a or in between. We need to notice, we need to take care of this. This is very important. So there is not an and, there is an or. So z can either be less than equal to x or z can either be less than equal to y, and still it would be a possible candidate for answer. And x is not a multiple of z and y is not a multiple of z. X is not a multiple of z and here now we have an and y is not a multiple of z. So basically, since first thing that we can straight away do is, since we are given these two conditions, x is not a multiple of z and y is not a multiple of z, we can simply make these two conditions as z is less than x and z is less than y, because simply x is not supposed to be a multiple of z, right? And if we take z as equal to x, then x is now a multiple of z. So basically we can say that z is less than x and z is less than y. So now let's see that further we need to, in this question, find the maximum possible value of GCD AI comma AJ. So basically we need to find maximum value of GCND AI comma AJ for all pairs. So let's see the test cases. The first test case is 285. So basically, since there are only two numbers, so we don't really have a choice here. So what we can do is simply GCND 8, 5 would be the answer. Now we need to find the GCND 8, 5. So let's first let's first through these conditions let's first through these conditions find out all the possible candidates for z. So we know that z must be less than x and or z must be less than y. So simply the possible candidates for z would be 1, 2, 3, 4, 5, 6, 7. That's it. So yep. And also, okay. So condition for z is, and we have these numbers as well. So we need to find the best option out of these. So obviously, since we need to find the greatest possible value of z, we will start checking from the end. So let's check for 7. So 8 is not a multiple of 7 and 5 is also not a multiple of 7. So answer for this test case would be simply 7. So the answer for first test case is 7. Then the next test case is 666. Again, since all the elements are same, we don't really have a choice, and the answer would be GCND of 6 comma 6. So again, the possible candidates in this test in this case would be 1, 2, 3, 4, 5. And we will again start checking from the right, and we see that 6 is not a multiple of 5, and this 6 is also not a multiple of 5. So answer for this test case would be 5. Then the next case is 8, 9, 8, 8, 2, 8, 9, 8, 8. So GCND. Now we have two possible combinations. We can either do this or we can do this. GCND of 8 comma 9. Basically, if we take these two and if we take these two, we have two possible different pairs that we can get in this array. So let's find the answer for both. So GCND 8 comma 8, the possible candidates would be 1, 2, 3 till 7. And we'll start checking from the right again, and we see that 7 is not 8 is not a multiple of 7. So in this the value would be 7, and GCND of 8 comma 9 would be 1, 2, 3, 4, 5, 6, 7, 8, 8. So we'll start checking from the right. Now we see that 8 is not possible because this 8 is a multiple of 8. So this cannot be the answer. Then 7, 9 is not a multiple of 7, and 8 is also not a multiple of 7. So, yep, 7 is a possible value. So this is also 7. And since both of these are 7, the answer for this would be 7. The answer was initially maximum of these two. So basically, one observation from this solving this particular value was that simply GCND of x comma x would be simply x minus 1. Since if we are taking GCD of x comma x, the possible candidates are 1, 2, 3 till x minus 1, right? And when we start checking from the right end, the first value that you will check is x minus 1. And we can say that x can never be a multiple of x minus 1. So we can say that x can never be a multiple of x minus 1. Why? Basically, x remaindered by x minus 1 or x modulo x minus 1 would be, we can write this as x minus 1 plus 1 modulo x minus 1. And then we have this property a plus b modulo m is equal to a modulo m plus b modulo m whole modulo m. So using this property, we can open this equation. So this will become x minus 1 modulo x minus 1 plus 1 modulo x minus 1 and whole modulo x minus 1. So this value will be 0 and this value will always be equal to 1, since x minus 1 is always greater than 1. Because in the question we are given that x is greater than equal to 5 and y is also greater than equal to 5. So basically x minus 1 would always be greater than 1. In fact, x minus 1 would always be greater than 4, greater than equal to 4. So basically this will be a higher number than 1. So this will always be equal to 1. And again this comes out to be 1 modulo x minus 1. So this is again 1. So we know that x modulo x minus 1 is always 1. So x can never be a multiple of x minus 1. So we have this property, and using this property we can say that GCND of x comma x is equal to x minus 1. Now let's try to analyze the other cases. So here also same, we had GCD of 6 comma 6. Now let's see what happened when we had two different numbers, GCD of 8 comma 5. So basically, again, just what we saw, that x modulo x minus 1 is always 1, right? We saw this. So here also, let's say that for the higher number, whatever is the higher number among these two, this would be higher number minus 1. This would be, let's say that the x is higher, x is greater than y. Let's just assume this, because GCND of x comma y is literally the same as GCND of y comma x. So we can just assume the first element to be greater. We can always make sure that the first element is greater, because let's say we had GCND like this, so we can just write this as GCND of 9 comma 8. So let's just say that the first element is greater. So this value would be x minus 1, right? So we always know that we know that x is not a multiple of x minus 1. So now we only need to make sure that this is also not a multiple of x minus 1. And if y is also not a multiple of x minus 1, then simply this would be the answer. And this is the highest possible value that can be the answer. So this will be the final answer. So basically, let me more say my statement more formally. If we have GCND of x comma y, and we know we are saying that x is greater than y, then the possible candidates are 1, 2, 3 till x minus 1. And we start checking from the left, right? So basically we will check for x minus 1, and if we check for x minus 1, we know that x cannot be a multiple of x minus 1. And we also know that y is less than x. So y is less than equal to x minus 1. So we now have two cases, GCND x comma y will have two cases. One is when y is equal to x minus 1, and one is when y is less than x minus 1. So when y is less than x minus 1, y modulo x minus 1 would simply be y, which is non-zero since we are given y greater than equal to 5 when y is less than x minus 1, right? So basically in this case, the answer we will again get x minus 1. And we also saw that previously, in this case also, the answer was x minus 1. Now we have one case remaining. So when y is equal to x minus 1, we know that now x minus 1 cannot be an answer because y is a multiple of x minus 1. So we will check for x minus 2. Now again, when we check for x minus 2, x modulo x minus 2, again, just like how we did previously, we can do like this, and this will become 2. So x modulo x minus 2 is also never 0. So x can never be a multiple of x minus 2. And we know that y is equal to x minus 1, right? So let's see if y can be a multiple of x minus 2 or not. So y modulo x minus 2, this will become x minus 1 modulo x minus 2. This will again using that same trick, x minus 2 plus 1 modulo x minus 2. We can say that this is also 1. So y also can never be a multiple of x minus 2. So in this case, now we know that the answer is x minus 2. So let me rewrite these equations. So we found out when GCND of x comma y, there are two cases. When y is equal to x minus 1, then answer is x minus 2. And when y is less than x minus 1, then the answer is x minus 1. right? Yep. And the other case is GCND of x comma x. So in this case, the answer is always x minus 1. And we are saying that x is greater than y. So these are the, we have basically solved this GCND function. And now we need to find our original problem was to find maximum value of GCND AI comma AJ. Right. Our initial goal was to find the maximum value of GCND AI comma AJ. So basically, if there are only two elements in the array, then we can say that we know that like in the first test case, since there was only 8 5, right? So GCND was literally 8 5. The only possible answer was this. And again in the next test case also there was only one possible value of GCND. So basically what we can say is we can write it like this: the two special cases, if there is only one unique value in array A. So basically this corresponds to the case 666, this case. So in this case, simply the answer would be that value minus 1, because we have only one possible option and we will need to use this function. So answer of this is x minus 1. So answer in this case would be ai minus 1. And since there is only one unique value in the array A, so ai's are all same. Then the next case will be if there are only two unique value in array A. So again in this case, basically let's assume that x and y are the two unique values. So again we can simply follow this function to get our answer. So GCND of x comma y will be our answer. Now let's see when there are more than two unique elements. So now we will start to get multiple choices in our answer. We will have multiple GCND AI comma AJ as our potential answers. So basically we need to now maximize this, right? So one thing we can observe is GCND x comma y directly correlates with x only. It does not really depend that much on y. Basically, if x is higher, then GCND x comma y is also higher. X minus 1, x minus 1, x minus 2. And x minus 2 is only in case when y is equal to x minus 1. Only in this case, right? So what we can do is we can take the GCND of maximum element and minimum element. What is this doing? Basically, we saw that the maximum answer using this function, the maximum value of this function can be x minus 1, right? In all the three cases, the maximum value can be x minus 1. So what we can do is we can try to get the maximum element minus 1 as our answer, because this will be the highest possible answer over all pairs. So maximum value minus 1, we can try to get this as our answer. So if we need this as our answer, we can do two things. If we either have two of these in the array A, we can simply do GCND of x comma x and the answer would be x minus 1. Or we can find a y for the maximum element that is less than x minus 1. So if there exists a y that is less than x minus 1, then also we will get x minus 1 as our answer. So basically, to check if there is a y that is less than x minus 1, we can simply check with the minimum element. If minimum element is less than, because minimum element has the highest chances of being less than x minus 1. So this can be the answer if minimum element is less than maximum minus 1. And the value of this would be maximum minus 1, since this is and this is the highest possible value that we can get. So uh, we had we said that we were solving for the case when there are more than two unique elements, right? More than two unique elements. So basically, let's say that there are k unique elements, a1, a2 till ak, and I have written them in ascending order, right? So ak would be the maximum and a1 would be the minimum. So a1 has to be less than ak minus k minus 1, I think. Let me just 1 2 3 4 5. So 5 minus 4, so k plus 1. Okay, a has to be less than equal to this, because we know that they are all distinct, right? They are all distinct. So if we know that the maximum element is ak, the highest value that the second maximum element might get is ak minus 1 and then ak minus 2. These are the highest possible values they can attain if they are all distinct. So the smallest element has to be ak minus k plus 1 for k unique elements. And if we are saying that k is greater than 2, so this would be, we can write this as ak minus k minus 1, and k minus 1 would always be greater than 1. So ak minus k minus 1 would always be less than ak minus 1. Basically, first we multiply by minus on both sides, so this becomes, and then we add ak, so this becomes this. And this is nothing but the minimum element. And this is nothing but the maximum element minus 1. So we can say that if there are more than two unique elements, the minimum element is always less than maximum element minus 1. So basically this condition is always true. Minimum element is always less than maximum element minus 1. So the answer in this case would always be maximum minus 1. So we have solved all the cases for this question, and we can simply, I'll show you guys the code for this now. I think this was the solution. So basically what I'm doing is I'm taking the input and inserting them in a set, because I need to know the number of distinct elements, right? So I'm inserting them into a set, and then if there are more than two distinct elements, then simply the maximum element minus 1 would be the answer. If there is only one unique element, then simply that element minus 1 would be the answer. Else, if there are two unique elements, then we can simply take a and b, and we can apply this function. So basically, GCND of x comma y would be the answer. So we can apply this function if a is not equal to b minus 1. So if y is not equal to x minus 1, then x minus 1 would be the answer. So b minus 1, and else a minus 1 would be the answer. So this was the solution for problem C. The time complexity would be n log n since we are inserting in a set, and these are all O of log n operations only. So overall time complexity would be n log n, which is well within the time limit. So let's move on to the next problem. So cycle and add. You are given two arrays B and D, both of length n as well as an integer C. You also have an array A of length n initially filled with zeros. You would like to make the arrays A and D equal to each other. To achieve this, you can perform the following types of moves. I'm audible, right? Let me just check once. Hello, hello. Okay. So cyclic shift the array, write one step, that is this to this. Thus, this operation has a cost of C. Choose an index I and add 1 to AI. This operation has a cost of BI. So each type of operation can be performed as many times as you like, including zero, and the operations can be performed in any order you like. Find the minimum cost of making the arrays A and D equal. It can be proved that it's always possible to achieve this. So problem D. Basically, we are given two arrays B and D and an integer C and an array A initially a 0. So we have an array B comma D array, and we have a value C, and array A is initially all zeros. And what we need to do is we need to transform A into D using some operations. And these operations are defined as followed. So basically, in one operation, we can either cyclic shift the array A right one step, and this would be a this would have a cost of C. So cost C, basically cyclic shift on A. So if A looked like this initially, then after this operation, it would look like this. And then the other type of operation is, for this, the cost is BI, and AI becomes AI plus 1. Right. Let's see the time constraints for this problem. Uh, so we are given t is less than equal to 1000 and n is less than equal to 2500. And we are also given that sum of n over all test cases won't exceed 2500. So basically, uh, n square solutions can pass because 2500 square operations would be 625 into 10 to the power 4, which is 6.25 into 10 to the power 6. And we are allowed 1e8 operations in 1 second, so we can do these many operations. So expected time complexity would be O of n square, or we can maybe also do O of n square log n. Although this would be a lot more difficult to pass since log n would be around log 2500 would be around mm, 2 to the power 10 is 1024 and 11 is 2048. So somewhere around 11 point something. So this would make the number of operations almost very close to 1e8. So n square log n would be difficult to pass. So we'll try doing it in O of n square only. So let's see the test case. The first test case is basically we are given n and c and then the arrays b and d. So n is equal to 3, c is equal to 2, and b is 3, 5, 4, and d is 1, 2, 0. Right. And initially we have a as 0, 0, 0. Right. So one thing we can do is basically just ignore this operation and simply use this operation only. So just using this operation in order to transform A to D, what we can do is uh, we will add plus 1 on this once and plus 1 on this twice, and we don't need to perform any operation on the third element. So basically the total cost would be, here we will have 2 into 5 since the cost is bi for incrementing ai. So 2 into 5 and 1 into 3. So 3 plus 10, 13. So the overall cost for this is 13. Now what we can do is we can try to use the cyclic shift operation, right? So how can we benefit from the cyclic shift operation? So we know that this element has a lower cost. When we increment on this index, it has a lower cost, right? So what we can do is let a initially be 0, 0, 0. We can follow this strategy. We can first do two operations on this index. So this would cost us 2 into 5, which is 10. And our a will now look like this 2, 0, and 0. So now we can do a cyclic shift, right? So after this cyclic shift, the array will now look like this. And then we need to set this element as well, right? So 1, we will again perform one operation on this. So the cost of that would be 3. And we also perform the cyclic shift. The cost of that is 2. So the overall cost in this case would be 10 plus 2 plus 3, which is 15. Oh, sorry, my bad. This is not 2 into 5, this is 2 into 3. Sorry. The first index is corresponding to 3 BI value. So this would be 6 plus 2 plus 3, which is 11. So we are, this is the most optimal way we can solve this test case. So the answer would be 11. Let's see the next test case. 3, 4, 2 and 2, 1, 3. So 3, 4, 2 and 2, 1, 3 with c is equal to 2. And initially our array A would look like this. This is our array B and this is our array D. So one thing that we can do is simply not perform the cyclic shifts and just use this array to get to transform array A to array D. So we can do plus 2 on this. We can do plus 1 on this and we can do plus 3 on this. So this would require 2 into 3 coins cost. This would require 1 into 4 cost. And this would require 3 into 2 cost. So this is 6 plus 6, 12 plus 4, 16. Now let's try to use the cyclic shifts. So A is initially 0, 0, 0. What we can do is we can do plus 1 on this index and this will become 1, 0, 0. with a cost of 3. And then we can perform one cyclic shift. So one cyclic shift, it will become 0, 1, 0, and this will be cost equal to 5, right? So we need a 2 and 3 as well. So we know that this has the best possible cost, right? This element has the cost of 2. So applying operations on this element is very better, very good. So what we can do is, since we know that after the cyclic shift, this element will go here and this element will come here. So before doing the cyclic shift, we can perform this as well, plus 3 on this element. So this will become 103, and that will be cost 3 plus 3 into 2, which is 6. So 9. And now this 5 will become 11 because C is equal to 2, right? So this 3 will come here and this 1 will go here. This 0 will go here after the cyclic shift. So the array will look like, oh, my bad. Basically, we need 3 in the end, right? So instead of performing the operation there, we can perform the operation now, since at this point the least cost would be used. So 0, 1, 3, and then cost would be 5 plus 2 into 3, 2, right? Yep. So 11. And we have further one more element that we need to set. So since after the cyclic shift, this 0 will come here, right? So what we can do is, before the cyclic shift, we can perform plus 2 here, so that this becomes 2 and the cost will become 2 into 2. So plus 4, and this 2 will come here. So this will become 2. So basically, this will be the least amount of cost. How? Since we made the 1 and 3 using the best possible value in the array B, and the value of C was quite small, so this comes out to be the best, most optimal answer. Although there might be cases where the value of C can be very large, so we would have to avoid doing these types of things. Basically, if C was quite large, if C was 10,000, so basically this will become 10,003 or something. This will become a large number. So basically, performing the cyclic shift would be bad, and we can just use directly the B values. But here in this case, the value of C was quite small, so we got our optimal answer from performing the cyclic shifts. So let's try to analyze what all costs I can use to set a value in certain case. So let's try to analyze for n equal to 4, right? The array A would initially look like A1, A2, A3, A4, right? And let's they are all equal to 0 initially. They're all equal to 0. So let's say that we are performing 4 cyclic shifts. No, let's say we are performing 3 cyclic shifts. So after the first cyclic shift, what will happen? The array will look like A4, A1, A2, A3, then A3, A4, A1, A2, then A2, A3, A4, A1. So if we are assuming that we will get our optimal answer using 3 cyclic shifts, we need to make sure that in the end this is equal to D1, this is equal to D2, this is equal to D3, and this is equal to D4. And we can perform the B operations in between. B operations here. We can perform the B operations here. We can perform the B operations here. So we can perform the B operations and between, and in the end we need to get this as the final array. So if we are fixing that we are performing three cyclic shifts, we will now try to set each value with the least possible cost, right? We will try to use the V values which are the lowest, which we will try to use the operations that are less costly. So we know that we need to set A3 equal to D2, right? So we can see that in our array, A3 was initially here, A3 was then here, and A3 was then here. So what we could have done is, we could have either set the value of A3 here, we could have done plus B3 into whatever D2, or we could have done the operation here plus B4 into D2, or we could have done the operation here plus B1 into D2. So all of these would have made the value of A3 equal to D2. So since we need to minimize the cost, we will be selecting the minimum of these three. We will be selecting the minimum of these three. So this would be minimum of B3 D2, B4 D2 and B1 D2. Right. This would be the minimum of all these. And similarly, what we can see is again we need to set A4 equal to D3, right? So we could have set the value of A4 here or here or here or here. Also B2 D2 also will come here. We can also set the value of A3 in the end as well. So similarly for A4 also, all four costs will again come. So minimum of this would be B4 D3, B1 D3, B2 D3, B3 D3. So B4 D3, B1 D3, B2 D3, B3 D3. So basically similarly for this also we will calculate, and similarly for this also we will calculate. And if we add all of them and we do plus, since we are doing three cyclic shifts, 3 into C, so this would be the most optimal answer for three cyclic shifts. Okay, so this is one thing. So if we find out the answer for, if we find out the most optimal answer for all cyclic shifts 1 till n minus 1, 1 till n actually, because after n cyclic shifts the original array will come back, because if I perform one more cyclic shift then again A1, A2, A3, A4 will only come back. So we don't need to perform more cyclic shifts after that. We'll just be repeating the operations. So if we find out the most optimal answer for all cyclic shifts 1 till n, we can take the minimum of that as answer. But let's analyze the time complexity that we are requiring to find this. So basically for calculating for one cyclic shift, for each AI, for setting the value of each element, we will be needing to take the minimum of n elements. A maximum of n elements we will be needing to take the minimum of. So finding the cost for setting A3 equal to D2 itself is O of n. And then for each value is, it is O of n. So overall, O of n square would be the time complexity that we require to naively find the cost for a particular number of cyclic shifts, right? So overall for n for to finding the answer for all cyclic shifts 1 till n, we will require O of n cube complexity, and that will not pass. We can write a solution of maximum O of n square complexity. So we need to further improve this process. So let's take a bigger array and analyze it more. How can we improve this? So let's take n equal to 5 and cyclic shifts as 3. So initially array A1, A2, A3, A4, A5. Then it becomes A5, A4, sorry, A1, A2, A3, A4. Then it becomes A5, A4, A1, A2, A3, sorry, A4, A5. Then it becomes A3, A4, A5, A1, A2. So, yep. And we can perform the operations in between B type. So in the end, we need to make sure that this is equal to D1, this is equal to D2, this is equal to D3, this is equal to D4, this is equal to D5. We need to make sure this. So again, we know that let's take for any element, let's take for A1. To make A1 equal to D4, we can either perform the operation here or here or here or here. So we will need to take the minimum of actually B1, B2, B3 and B4. B1, B2, B3 and B4. We'll need to take the minimum of this, right? Similarly, for A5, we can see that we can either perform the operation here, or we could have performed the here, or we could have performed here, or we could have performed here. So we'll need to take minimum of B5, B1, B2, B3. So again, this will require O of n, and we need to do this for n elements. So O of n square, and we need to do this for n different values of cyclic shift. So O of n cube. So we cannot do this. Let's try to see what happens in case of cyclic shifts 3. Cyclic shifts equal to 3. Let's take the color blue for this. Okay. So in this case, we need to make this as D1, D2, D3, D4 and D5. Right. So now let's take A5 and A1 only. So the possible places where we can perform the operation on A5 will be here, here or here. So we can see that if we know the minimum of here, we will have to calculate the minimum of B5, B1 and B2. And when we are taking cyclic shifts equal to 3, we were finding the minimum of let's take yellow for that. Minimum of B5, B1, B2 and B3. Basically, this extra was added. So what we can do is we can use this since we are recalculating this in the next value of cyclic shifts. Since we are recalculating, because we already know minimum of B5, B1 and B2 if we have found the answer for cyclic shifts equal to 2. So we can simply use that instead of this, and this will now become O of 1. So this will improve our complexity from n cube to n square. So what we can do is, since we are recalculating things here, we can use dynamic programming, and it is very simple. Let's say that dp of I comma j represents the minimum value for setting the ith element, whatever it may be. In this case, if I is equal to 3, then this pair. basically in one based indexing. If we take zero base, this is I is equal to 0, I is equal to 1, I is equal to 2. So I equal to 2, minimum value for setting the ith element, sorry, minimum value for setting the jth element, and this will be j equal to 0, j equal to 1, j equal to 2. When we do uh, I cyclic shifts, we can kind of use this as the sub problem, because we can then use the values that we have previously calculated. So if we have calculated this, right, so what will happen? dp of the yellow one, basically this corresponds to the value dp of 3 cyclic shifts and 0 1 2 second index, setting the second index of 3 after doing 3 cyclic shifts. So we can use the sub problem of dp of 2 cyclic shifts and setting the second element. So uh, this is the 2 cyclic shifts, right? And setting the second element, I made a mistake here, I'm sorry. The second element is this, and let me remove this. So basically, this would be minimum of B1, B2, B3. I'm sorry for that. This would be minimum of B1, B2, B3. Minimum of these three, and this would be the new addition in the fourth cyclic shift, third cyclic shift. B5 would be the new addition. And we can take another case actually that will make it more clear. Let me erase this. Sorry. Let me erase these. Let's try setting the fourth element in cases 3 cyclic shifts and 2 cyclic shifts. So if we set the fourth element, so let's try setting the fourth element. So we could have performed the operation here or here or here or here. So that would be minimum of B1, B2, B3, B4. And in case of 2 cyclic shifts, uh, let me take yellow for that. We could have performed the operation here or here or here. So that is minimum of B1, B2, B3, B4. B2, B3, B4. So basically, we can recalculate, we can reuse this. We can reuse this here. So dp of 3 comma 2, basically 3 cyclic shifts and setting the second element. We can reuse the value of 2 cyclic shifts and setting the second element. So we just now took the case for 0 1 2 third element, right? So this is zero based indexing. So let me write 3 only here. And the extra value would be the extra value, basically this will come here, this will come here, and this will come here, and this would be the new extra value that we need to take the minimum of. Basically B1 here, in this case B1, in this case B5. So this comes out to be the extra value. So we can easily take the minimum of this comma basically B of j minus I. How j minus I? So we are setting the fourth element, right? We are set third element, and 3, basically we need to in the first cyclic shift, that is the new additional value that we need to take minimum of. The in the first that we had, that is, this is the additional value that we need to take the minimum of. So this was I cyclic shifts ago. So basically if the current position is j, then j minus 1, j minus 2, so this would be the j minus ith position. So here in this case it would be 3 minus 3. So 3 minus 3, which is 0, b of 0. And in case where we were finding for the second element, so dp of 3 comma 2 is equal to minimum of dp of 2 comma 2 comma 2 comma b of j minus I, which will be minus 1. So this minus 1 basically means that one cyclic shift, sorry, one cyclic shift, another cyclic shift, and then another cyclic shift back. We are basically going backwards. So 3 minus 2 minus 1 1, 1 minus 1 0, and then 0 minus 1 minus 1. So basically we are going I cyclic shifts back. So j minus I is minus 1. Minus 1 basically means the last element. So we can basically formalize this like this, that dp of I comma j would be equal to minimum of dp I minus 1 comma j comma we need this also, right? We need to now add this element, the first initial array corresponding to that b value. So what we can do is b of j minus I, and to adjust the indexes we can do a plus n and modulo n. And since we need to set the value to dj, we can simply multiply dj. So now this becomes the cost. This will store the cost into dj. So this transition will give us the minimum of okay. So this transition will give us the ith cyclic shift, the cost of setting the jth element. So now what we can do, we can calculate this dp fully in O of n square, and then for each cyclic shift we can just do sum of j equal to 0 till n minus 1 dp I comma j. This will give us the answer corresponding to I cyclic shifts. So, and we can take minimum of this overall for all I. So that would be the answer. And since we need a base case would be dp of 0 comma j, which is simply when we are not performing any operations, when not performing any cyclic shifts. So simply we will do bj into dj. So this will be our base case, and we can calculate this dp, and then we can take minimum of this. So that would be our answer. So I'll show you guys the code. So I take input vector b and d, then dp of 0 comma I is bi into di. This is the base case. And then I run two for loops, basically for calculating the dp table. And I apply the transition dp I comma j, I minus 1 comma j, and dj into b of j minus I plus n modulo n. And for finding the answer, I am taking the minimum of sum over all i's, sum over all j's for each I. So here, this is the initial answer, and then I will calculate the current answer for all i's, and then take minimum of it. And also I into c will come, which is basically the cost of performing I cyclic shifts. So another thing here, sum of this plus I into C. This is separate. Let me just, I into C plus this. Basically, since we are doing I cyclic shifts, this is the additional cost. So I cyclic shifts and then the current cost, and taking minimum of that would give us the answer. So this, and the time complexity, since I need only two for loops, so it would be n square. And since I comma j depends on I minus 1 comma j, so I'll run the for loop from I equal to 1 till I equal to n. Since this way I'll have calculated the previous states, and j doesn't really matter. I could have run the for loop from n till 0 or 0 till n. It would be the same. So that was it for problem D, and we will end the discussion here. Thank you.